My name is Jessica Finzen. I'm a professor of mathematics in Bonn, and I'm a member of the scientific committee, and I will guide you through the morning session. So it's my pleasure to introduce our first speaker, Dennis Sullivan. Dennis Sullivan is a distinguished professor at Stony Brook and also an Einstein Chair at CUNY Graduate Center, and he has received numerous awards, including the US National Medal of Science, the Steele Prize for Lifetime Achievement, the Wolf Prize, and the Abel Prize in 2022. That's why he is here. Let me quote from the Abel Prize. He has received the Abel Prize for his groundbreaking contributions to topology in its broadest sense, and in particular its algebraic geometric and dynamical aspects. He's also a member of the US National Academy of Science, the New York Academy of Science, and the American Academy of Arts and Science. And today he will present us a Blackboard talk, so that's the usual way mathematicians in my area give talks. And he will tell us about three-dimensional fluid motions and long compositions of three-dimensional volume-preserving mappings. Stage is yours.
Can you hear me? Yes? Okay. So let's see. I'm going to give a Blackboard talk, and it's about something I heard about in the early 90s. I heard that as part of a lecture that the mathematical model in 3 dimensions of the motion of fluids, let's say incompressible, so a piece of fluid can change shape, but its volume stays the same. The general theory, even though it was well known and well understood since the 1920s, not well understood, but well known at a basic level, was known in dimension 2. In dimension 3, it was not understood even at the basic level. Nor was there a general theory for understanding the 3-dimensional fluid motion, incompressible. And to crystallize this lack of knowledge, their specific question was, if you take the mathematical model, which is called the Navier-Stokes equation, partial differential equation. I'm not going to write the equation. I'm going to talk about the model. If you start with an initial condition, which you think of, you have information about the fluid at some moment in time, which way it's moving, and et cetera, then does it evolve according to the mathematical model for all time, or does it actually blow up in some finite time? Does it always evolve for all time? That's a specific, precise math question about this particular mathematical model. And that's the question. And I heard this question in the early 90s, and I was quite surprised because, are these being used? They're being used? No? Okay. I keep seeing these space war things coming at me, so. Okay. So, what am I talking about? Okay. I was surprised by this lack of knowledge in 3 dimensions because, we live in 3 dimensions and, there's all this mathematics and physics about our reality. And I was surprised this wasn't known because, first of all, it was a precise math question. It didn't have a counterexample. It didn't have a proof. It's a precise math question. And yet we have all sorts of experimental evidence. And for example, when I was an undergraduate, well, there are 2 big reasons for this. One was just my experience. When I was an undergraduate in my state of Texas, where I grew up, I worked in the summers at the oil industry, and I knew that they used this model to increase the production of oil, and it worked perfectly. So that was one thing. And then in my studies of math, I sort of knew, after some study about this problem in the early 90s, I knew that in dimension 2D, the answer was yes. The smooth initial conditions evolve for all time. So, and the method of proof in 2 dimensions was based on what was my favorite theorem, and at the time, which is called the Riemann mapping theorem, which, let me just state the Riemann mapping theorem. So the professor one day at Rice drew this picture and drew this picture and said that there is a mapping Z, and f of z is here and z is here, and this can be any shape. This is the round shape, and f of z is the complex analytic mapping, which is what we've been studying in the course. And you know, if you take a small circle around z, it'll map to something that looks very round around f of z, possibly rotated and dilated. So this piece of material can be stretched and compressed to make it round in such a way that in every point, the round disk is just rotated and dilated, or rotated and compressed. And moreover, if you just take one point on the boundary and one point in the interior, and you say this point goes to this point on the boundary, and this point in the interior, say, goes to this point, then the mapping is unique. And I was sort of blown away by this statement. I was a chemical engineer at the time, and this is in the sophomore year of college. And I was sort of blown away by this statement because it's like so general. This is any shape. This map is essentially unique, and is unique if you specify these conditions. And I thought of math as sort of like formulas, computing integrals, and substitution, and you know, clever techniques and computation. And here was sort of a general statement that was clearly very deep, and I was suppressed, and so I like this very much, and changed my major to math. And then also, when I heard about this problem in the 90s about the three-dimensional fluids, and hearing that and learning that it's in 2 dimensions the problem goes away, and the fact that in 3 dimensions it was used successfully, and the fact that the thing was true in dimension 2, and the proof actually used there's a proof that sort of starts to slowly change this domain and move it into this domain. And that proof uses something in analysis about the local structure of such motions. And it's very closely related to this. I mean, this Riemann mapping theorem, and it's the continuous motion that does it, is very much like the meaning of the fluid equation. It's sort of analogous. It's not at all the same, but it's sort of analogous. And so I was intrigued by the fact that in 3 dimensions, we have a precise question which doesn't have an answer or a counterexample. Yes, it doesn't have an answer, yes or no. The statement is open, and it's still open at this time. So this is like over 30 years ago. Okay. I have trouble giving a lecture from notes because I want to just talk. So, okay, read here. So, been thinking about this more or less continuously since then. And so the first thing is, well, there's nothing in dimension 3 like this f of z study. This is theory of one complex variable. It's extremely rich, goes forever, and it's connected to many things. And there's nothing like that in dimension 3 as far as we know. That's the first point. So maybe if you study this problem and find out how it works, maybe you'll find something in dimension 3 that is as interesting and important for mathematics as the theory of complex variables in dimension 2, because it's closely related to the question, although it's not in an obvious way, just the techniques are. So that's one idea. And an idea that has, another idea is that you've all heard about Perelman proving the famous Poincare conjecture in dimension 3, and he used partial differential equations to do that. And when I first saw that, I got very excited because he dealt with singularities that were developing in that problem, in that partial differential equation. And then, in fact, when you looked at the second derivative of the equation he was studying, it was in form very similar to the Navier-Stokes and Euler equation here. You have two names here because the Navier-Stokes equation has a friction or diffusion aspect, like Brownian motion. And the coefficient of that term is, when it's 0, is called the Euler equation. I'll come back to that. So maybe the theory in dimension 3 of, I've been very preoccupied with the question of classifying closed manifolds in various dimensions. And there was a beautiful picture that arose around 1980. Thurston was constructing many manifolds with non-Euclidean geometries, and he had a whole picture of all three manifolds, which was finally proven 25 years later by Perelman with a nice story in between. And so there's something very special about dimension 3 in terms of all the dimensions studying manifolds. So last few years I've been thinking about that proof and trying to find something in there which is vaguely like complex variables in dimension 2. And well, that's still an ongoing project. There's something special about dimension 3, but we don't quite know what. So but I invite any of you to try that idea. But then I sort of don't like to think about equations and solving them. I want to know the meaning of things, and there's something about this model when there's no friction or no diffusion term. It's called the Euler equation. And what I liked about this was that you could, this special case of the whole problem. The whole problem has a parameter in it. How much viscosity and diffusion do you have? The parameter 0 is called the Euler equation. Anyway, what I liked about it is you could say what the Euler equation is. Okay. Looking at the time. It's like, a 007 movie where the clock is ticking down and he has to dismantle the atomic bomb, and then it stops at 0.007, right? Anybody to see that movie? I feel that. It's sort of anyway. Let's see, what am I saying? Okay. So the structure of the equation, when there's no diffusion, so you can just say it in a math sentence. So here's the structure of the equation. I'll just draw a picture and then say the math sentence. So the fluid is moving along, and in German you call it rot, and in English you call it curl. You think of the velocity field of the fluid, you take its curl or its rotation, rot in German. How do you say it in German? Rot? Huh? Somebody say it. Louder, I can't hear. I really can't hear now. Okay, rot, okay. Anyway, rot, I don't know, rot. Okay. Anyway, it really means rotation. It's the movement is like going this way, and it's in dimension 3, the characteristic polynomial of a matrix is cubic, so it has to have one real root at least. So there's a direction of the motion, and then there's another direction, it's not the same, on which the fluid is rotating. It's sort of going this way, and it's rotating like this way. They could line up, they don't have to line up. And then, but these lines of rotation, I've sort of drawn some here. These are like, you could think of the fluid is filled with these other lines where it's rotating. And this is called the vorticity. So this is a picture of the vorticity of the moving fluid. And this is a mathematical object whose nature needs to be discussed. But whatever it is, the Euler equation simply says this vorticity is transported by the motion. So the fluid moves along, and this object, however you're supposed to consider it, is transported by the motion to the vorticity at the later time. And then that's transported by the motion to the vorticity at a later time. That's the equation. So I like this idea of transport of structure. I spent 20-odd years in France, and that's one of the main things I learned. The French have a good way of analyzing basic concepts, and transport of structure is one where you take any mathematical object and you can take any bijection between the underlying set, and you just transport the structure over by the object is defined with a lot of set theoretic considerations, like collections of subsets called open sets. That would be a topology, some algebraic structure, whatever it is, just gets transported over by the bijection, and you get another structure over here. So the fluid is moving everything along, and this vorticity is just transported by the structure. That's the Euler equation. Then you add a little randomness, and that's the equation. Does this process blow up in finite time, or does it continue forever if you started with a smooth enough initial condition, say the vorticity? So that's something, you can think about without writing anything down on paper. And this preoccupation with this vorticity and curves in space and how they link and not and so on helped Maura Chast and I in coming up with the work on string topology. But that's just an aside, but just by thinking about this, it was very natural to, in the diffusion case, these lines could become circles and they touch and they reconnect, which is basically what string topology is. So that was an origin of that. So now the question is, what is the structure of this thing which is transported? And so there's history in the 1800s. Kelvin and Helmholtz did two different things. Kelvin studied what was called the circulation around a closed curve. So this is the moving fluid. You just restrict it to a closed curve. You project it onto the tangent. And then you integrate that, and that get a number, and then this imaginary curve just moves along with the fluid. The velocity changes, you compute the new circulation, and that function of closed curves is constant. So that's another way to describe this transport of vorticity. And then Helmholtz came along and filled in this small closed curve with a membrane, and then studied how many of these vortex lines cut through the membrane. And that gave the same number by Stokes' theorem, whose name is part of the Navier-Stokes equation, which is the name of the model. And when there's no diffusion, there's 2 points of view here, but you can think of this as being a picture of what it means to transport the vorticity. So, so if you say it this way and think of Stokes' theorem, you could think of this as a picture. This picture of vorticity is the picture of a degree 2 differential form. Namely, that's something that you integrate over surfaces. So you integrate that over the surface to get the flux lines through, and then that gives you the circulation. It's the picture of a degree 2 form, a differential form on 3 space, so it's function times dx dy plus another function times dx dz plus another function times dy dz. And so it's 3 functions. And then you have to transform it like a differential form. So you have to look at the map, the flow map going backwards in time and pull the differential form forward. That's how you transport it. Okay, and that's the equation in all dimensions. But now in dimension 3, a 2 form, see in dimension 2, a 2 form is just sort of a volume form. So it's a different object. You don't have this picture. In dimension 3, a 2 form is also, it has this picture, and we're considering incompressible motion. So the volume is preserved. So that means you can, see the 2 form gives you not only these lines, which are the kernel of the 2 form. You have a 2 form, you put in a vector here and anything here. If this is equal to 0, for all vectors you put here, that's V is in the kernel. So this one-dimensional subspace at every point is the kernel of the 2 form. That's how this picture has come. And then when you restrict it to a transversal plane, you get a 2 form on a plane, which is a volume form. So we have a notion of how much twisting is going on in terms of this, or how much flux lines through any surface there is from this. But now there's something interesting in dimension 3 that you can do, which is you have the volume form, which is preserved. We're studying incompressible fluid motion, so you have a volume form. So then it turns out there's, at each point where this vorticity is non-zero, there will be a speed vector so that this two-dimensional volume form times this vector gives you the three-dimensional volume form. So if it's zero, you take the vector to be zero. If it's non-zero, you take it to be that. So the vorticity is also a vector field. By this procedure, the lines, the kernel of the two form, and the volume form give you this speed vector. Well, to a topologist, these are completely different objects. One is something that's contravariant in degree 2. This is, if you just say vector field, it's not even, it doesn't even transform under maps unless the maps are bijection. So it has completely different functoriality. But because the volume form, which was used to go from here to here, is preserved by all the mappings of the fluid problem, this vector field is meaningful. So we can think of transport of vorticity as being you transport the vector field. So this can only be done by a bijection. So you have to go back, take the vector field, and then bring it forward. It's like a conjugation operation. It's like the adjoint action in a Lie algebra of a Lie group on the Lie algebra. So it gives a completely different perspective. So when you write formulas, you don't see all this. But if you think about the meaning of the terms, you see this different aspect. Okay. Now, this the bicycle idea. Anybody can guess what I mean by the bicycle idea? You know, if you're going along on a bicycle and you're turning, you sort of lean in to turn. And if you took a picture, the bicycle would just be stopped and it's leaned over like this. If there were a bicycle like that, it would just fall over, right? What makes it stay up? Any ideas? What? No ideas? What makes a bicycle stay up? What? Okay, well, I mean, we had in our physics course the first year, we have to hold a bicycle wheel turning and with two handles, and then it's hard to turn it because of the angular momentum, right? Like a gyroscope. So this twisting of the fluid is sort of like a little bicycle wheel at every point that's turning. It gives the fluid some rigidity, resistance to deformation at every point. So it's like some kind of angular momentum, field of angular momenta, and it gives the fluid the structure of like an elastic solid because it resists motion where it's non-zero. And so the equation that says the vorticity is transported by the motion is saying this is an innate property of the fluid that gives it some resistance to deformation. And then the motion of the fluid is deforming this plastic medium. I'm now imagining it's like an elastic medium. It's not a liquid anymore. It becomes an elastic medium which has resistance to deformation. And then the motion is, well, there's a caveat here, but let me ignore it for a second. the motion is deforming this elastic medium. That's kind of a different viewpoint, but it means the same thing. Okay, so one idea is that we could So one idea is to think of the fluid as a plastic medium whose vorticity is giving it its resistance to motion, and this is part of the nature of the fluid. So yeah, for the last few years I've been wondering, the way this is always discussed in partial differential equations is they think of the state of the fluid as given by the velocity. And I'm sort of thinking that I'd like to think of it as the fluid, the vorticity is more innate to the nature of the fluid, and it's transported by the motion. This is sort of ignoring the diffusion effect, but just, you know, in the more ideal case. Okay. So now let's erase all the words, keep the picture. But now we're going to think of, so this is innate to the fluid. It gives it some rigidity, and it's transformed by the motion in the no diffusion case. And on the other hand, it can be in dimension 3D only. It can be thought of as a vector field. It's not the velocity field. It's pointing in this direction, which I've said before is not the same. The spinning direction is not the same as the motion direction. Okay? Okay, so now if you pick up any book or look at any paper on elasticity, theory of elasticity, it's often in dimension 3, of course, sometimes 2, then you think of this vector field that's the description of the vorticity, and then you can form, these are just 3 functions again, and you can form the Jacobian, I'll call it A. At every point it gives you a linear transformation from the tangent space at the point to itself, really. You can make the vector field wants to move a little bit, and it's telling you how to move the tangent space. This is the Jacobian matrix of the 3 functions. And then you form the symmetric part. You take it, the matrix plus its transpose, and we'll call this the deformation tensor. So this has 6 real parameters. It's a symmetric matrix. It has 6 real parameters at every point. And in the theory of elasticity, it's sort of telling you the strain on it's giving you somehow the vector field starts to try to, the motion tries to deform the thing, and this is its power. And it's counteracted by this vorticity. So I want to think of it that way. Let's see, what do I have yet? Oh, yeah. So you could think that, the fluid is made of a lot of little tiny regions, which are kind of called fluid particles. And there's a distance between every pair of particles. And then a deformation means after the movement, the distance changes somehow. It's deformed. Like you bend something, you change the distances between the particles, right? You bend something, right? So this tensor is giving you the derivative of the change of the distance between pairs of points. I mean, you have a 3-dimensional array of points and a 6-dimensional array of pairs of points, and the distance is a function on these 6 parameters. The 6 parameters here are like the derivative of that function. Okay. Now, one reason for spending so much time on this is sort of something happened long ago, 40 years ago, in the theory of 45 years ago, in the theory of complex variables. It turns out let me give a list of ideas here. So the first idea is think of the fluid as an elastic medium, okay, with the vorticity giving it its structure. And then in the theory of elasticity, you study the Jacobian of the motion. I'm going to be working on 3-dimensional space, which I want to have like a bounded space to work in. So I'm going to work in the periodic 3 space, which is R3 modulo the integer lattice in R3. So we're working in some kind of periodic space. There's no boundary, but it's just closed and finite. And so we have this fluid moving around in there, and has this, at every point, there's this deformation tensor, there's this vorticity that's resisting it, and this tensor moves the vorticity instantaneously, just new positions, and stretches it. Okay, now so one is led to think of the space of all Riemann metrics. Let me just say set of all Riemann metrics on T3. We start from the usual flat metric. We know what distances mean. And then somehow the deformation tensor of the motion distorts the distances, and so we have a new metric. So we can transport metrics by transport of structure as well. So we think of the motion as transforming the metric to a new metric. Now, I remember I was always surprised by this, hearing about it. When you take a metric and transport it by a map, you get a new metric. In fact, Thurston used to explain this by, I had little kids, so you imagine little kids' pajamas, which have the little feet in them, and then you sort of take your scissors and cut the feet, and you turn them slightly, and then you sew them back. Okay? So that could be a deformation of the metric. But it's funny now because if you put them on, the little kid's got his feet in the wrong direction. But anyway, when you transform a metric, this mapping between this metric and the transformed metric is an isometry. So I was sort of surprised by this, when you transport structure like this transport map is an isomorphism of whatever structure you're transporting. So it's not really the space of all Riemann metrics on the torus, because this transported metric will still be flat. The curvature will be 0 and it'll be flat, but it's sort of in a new coordinate system. Okay? So it's a little bit subtle. So it's really the set of all flat metrics on the torus I care about. But it's still infinite dimensional, but okay. And now this is going to be, and on here, this has really got my attention. There's something called the tautologous, let me write it bigger. tautologous metric, let's call R equals this, the set of all Riemann metrics, and I only have to worry about flat ones because I'm only transporting the metric by the fluid motion. There's a tautologous metric on R, which is the set of all metrics. Why is that? Well, a tangent vector is, to the space of metrics, means, well, what is a Riemannian metric? At every point, you have the tangent space, and then the Riemann metric is a positive definite inner product on the tangent space, another positive definite inner product here. And you have this field of positive definite inner products. Well, you can choose a coordinate system, and that just becomes a symmetric matrix with the property that all the unit sphere, every vector has non-zero length, so there's like a unit sphere in the metric. This is the inner product applied to the vector itself with itself. That's what positive definite means. This is the unit sphere. So at every point, it would be something against the background original metric. It looks like an ellipsoid. So it's really a field of ellipsoids. And this picture in dimension 2 is very much part of complex variable theory. That's why there's this connection. And now, if you take this inner product and you just add epsilon times a matrix like this, a symmetric matrix, so this is P is the positive definite inner product. So this is a point in the space of all metrics. Now, if we add any symmetric matrix times a small number, this will still be positive definite. It'll still be symmetric, and since it's positive definite, there's a definite lower bound on the length, and epsilon is small enough, it'll still be positive definite. So this is a tangent vector to the space of metrics. It tells you how you deform in the direction of this symmetric matrix, okay? So now, this is a symmetric matrix at this point, in fact, where this positive definite matrix is, so you can measure the size of it. In fact, this symmetric matrix involves the transpose. Well, I mean, the idea of the symmetric matrix is it gives a relationship between the tangent space and the dual space, but the dual space is isomorphic to the tangent space because of the metric we have. So this becomes a transformation, self-transformation of the tangent space, and then it's symmetric matrix, so it has eigenvalues, and this tautologous metric is just the logarithm of the maximum eigenvalue. So the tautologous metric is, I'll just write it here, it's the log of the maximum eigenvalue of the tangent vector. So this is like a Riemannian metric on the space of Riemannian metrics. Okay. So, just about at the end now of my time, that we'll discuss more in the workshop today. So let me erase this again. So we have this tautologous metric. We're thinking of the fluid as a medium. The metric, so now the vorticity and the metric become the things that specify the state of the fluid, not the velocity itself. And on the torus, there are certain rigid motions, which are translations. These are precisely the vector fields for which this deformation matrix is zero. So we're sort of working modulo rigid motions. So we're just studying the bending properties of the fluid. So now I'll close with, why do I care about this? Is because so I'm fixing, the volume is being fixed. So actually the 6-dimensional space can be refined to a five-dimensional space because the scale of the metric is being fixed by the volume element. So there's a natural five-dimensional space at each point, which is telling me there's different possible tangent directions. Okay. So now the idea, this is sort of the takeaway, the idea is to reapproach this question about fluid motion using this bundle of five-dimensional spaces over the space of the fluid and thinking of a point in each one of these spaces as a metric, and this metric is being moved along and telling how the fluid is being distorted. And this space has a natural property. It's really, at each point, it's just this homogeneous space, which is determinant 1, 3x3 matrices divided by the rotations. So this is 3x3 matrices has dimension 9. Take the determinant 1, so now it has dimension 8. Then you subtract off 3 for this, which is 5. So this is the five-dimensional space. And now this natural metric, the logarithm of the maximum eigenvalue, becomes this natural metric on this homogeneous space. And this is a non-compact group, but it's acting by isometries on this space. So when you change coordinates, this picture here is transported isometrically to the picture here. So this gives you a new tool for deriving inequalities related to this discussion. And that's what I'm working on now. And I'll stop here. So thank you.
Thank you very much. You even left us more than 7 seconds time. You even stopped more than 7 seconds before your time ran out. Wonderful.
Hello, 7. Okay.
Well, now it's not. Okay. Well, on the other hand, in the interest of time, let's defer questions to the coffee break. So we'll just continue now with the Spark session, and there will be coffee break afterwards, and then everyone is welcome to ask you during the coffee break. So thank you very much once more.